This is one of a series of short videos designed to support and enhance your understanding of some of the key concepts contained within A-Level Further Mathematics. If you have already mastered the basics of a topic, then the video should stimulate your thinking and provide further insight. The focus is on looking in a bit more depth at examples that can be tackled using knowledge gained within the curriculum. These examples are not taken from any particular exam specification and as such may go beyond what you need to know for your examinations. However, they all illustrate key concepts that will help you by giving you a more thorough understanding. In this video, I am going to look at proof by induction and use some interesting examples to highlight the principles and show how useful it can be. So if we do a quick run through of the basics of proof by induction. Starting with any proposition, the thing which we want to prove, there are 4 steps to a proof by induction. The first is to show that the basis case, usually the n equals 1 case, is true. The second is to assume it's true for the kth case. The third, which is the inductive step, is to show that it's then also true for the k plus 1th case. And the 4th step is to make a conclusion. For examination purposes, the examples used are often based on sequences and series, matrices, or divisibility. And I'm going to assume that you're relatively familiar with all of those. What I'm going to do in this video is look at 3 interesting examples of proof by induction that you may not have come across before. In the first example, I'm aiming to prove an inequality, and I want to prove that n factorial is greater than 2 to the power n for all integer values of n greater than or equal to 4. It's already a little more interesting than some of the routine cases, because for the basis case we need to set n equal to 4, because that's part of our proposition. If we then look at 4 factorial, which is equal to 4 times 3 times 2 times 1, we find that that's equal to 24. And then we look at 2 to the power 4, which is equal to 16. It's clear that 24 is greater than 16, so we've proved that the basis case is true. When we move on to the second step, we're going to assume that the proposition is true when n is equal to k. So we're going to assume that k factorial is greater than 2 to the power k. Moving on to the third step, we need to look at k plus 1 factorial. In this step, I think it's often useful to write down what you're aiming to show. So you're aiming to show that k plus 1 factorial is greater than 2 to the power k plus 1. And I'm just going to leave that over there as something to aim for. But I must make sure that I don't make use of this on the way. So, looking at k plus 1 factorial, I can rewrite this as k plus 1 times k minus 1 times k minus 2 and so on, all the way down to 1. If you look carefully, you'll see that this part here can be written as k factorial. So k plus 1 factorial is simply equal to k plus 1 times k factorial. Looking now at the 2 parts of this product, I can obviously say that k plus 1 is greater than 2, because k has to be greater than or equal to 4. Using my assumption from step 2, I know that k factorial is greater than 2 to the power k. So making use of both of these inequalities now, I can say that k plus 1 times k to the factorial is certainly greater than 2 times 2 to the power k, which means 2 to the power k plus 1 using a simple power law. and I've proved my aim. I've proved that k plus 1 factorial is greater than 2 to the power k plus 1. Therefore, my proposition is true when n equals k plus 1. My final step is the conclusion. I've proved the basis case for n equals 4, and assuming the inequality is true for n equals k, then I've shown it's also true for n equals k plus 1, and hence by mathematical induction the proposition is true. In the second example, I'm going to use proof by induction to show that the interior angles of a convex n-sided polygon sum to n minus 2 lots of 180 degrees. This is a well-known fact that you may have seen proved in several different ways, but probably haven't seen proved by induction, so here it is. Step 1, we need to think about the basis case. The basis case, the smallest n-sided polygon would be a triangle, so we need to look at the case where n is equal to 3. In the case where n is equal to 3, we know that the angle sum there is 180 degrees. And if we look at our proposition, we can look at 3 minus 2 times 180 degrees, which makes one lot of 180 degrees, and we've proved our basis case. We've proved that it's true for n equals 3. We move on to step 2, and we assume that the proposition is true in the case when n equals k. So here's my k-sided polygon, and it's a good idea to number the vertices to help us understand. So we've got 1, 2, 3, several more going round there, and we'll come to the k minus 1 and the kth vertex there. And we're going to assume that the angle sum here is equal to k minus 2 lots of 180 degrees. So all of the angles, interior angles, sum to this value. Moving on to the third step, so here's our n equals k case, and we need the n equals k plus 1 case. So if we number the vertices as before, all the way round to k minus 1, and we add one more vertex. So now we've got k plus 1 vertices, k plus 1 sides. Here comes the inductive step. If we slide the original polygon over to there, for the shaded area, we make use of our assumption that the angles total k minus 2 times 180 degrees. In order to get the angle sum for the whole k plus 1 polygon, we need to add 3 more angles. Those 3 angles form part of a triangle, so we know that they sum to 180 degrees. If we now have k minus 2 times 180 degrees plus 180 degrees, we can write this as k plus 1 minus 2 lots of 180 degrees, and we've shown that our proposition is true for the k plus 1 case. The final thing is to make a conclusion. We've shown that it's true for n equals 3, and if true for n equals k, our assumption here, then it's also true for n equals k plus 1, and hence the proposition is proved by mathematical induction. A really nice example, I think. In my final example, I'm going to look at something completely different, and I'm going to consider the tiling of a square grid with trominos, which are these shapes here. And in particular, I'm interested in a square grid that has side lengths of 2 to the power n. So it has 2 to the power n squares along that side and down that side. And we want to prove that we can completely tile any 2 to the n by 2 to the n board with these L-shaped trominos if we simply remove one single square. I've placed the square in the corner of the board, but in fact it could be anywhere. We begin the proof, as usual, with the basis case, and in this case we take n equal to 1. So here's our 2 to the 1 by 2 to the 1 grid, and it's clear to see with one square removed we can tile the rest of the grid with one tromino, leaving no spare spaces and no overlaps. So we've proved that the basis case is true. For step 2, we assume that the n equals k case is true. Now, although I've drawn this grid here with 2, 4, 6, 8, an 8 by 8 grid, what I'm really representing is a 2 to the power k grid. So it's 2 to the power k squares in that direction and 2 to the power k squares in that direction. And I'm assuming that if I remove one square, the whole of the rest of that grid can be completely tiled with a series of L-shaped trominos with no spaces left and no overlaps. So that's my assumption. What's really nice about this example is the visual aspect of the inductive step. So there's my assumed n equals k case. If I then look at the n equals k plus 1 case, so remember that this was a 2 to the k by 2 to the k grid. Here I've got a 2 to the k plus 1 by 2 to the k plus 1 grid. And given that this is two lots of 2 to the k, I've got a 2 times 2 to the k by a 2 times 2 to the k grid. I simply need to take my grid of size k and make 4 copies of that grid, which can all be completely tiled according to our assumption, and put those together to make the k plus 1 grid. But remember that our objective was to show that the whole of the k plus 1 grid could be tiled with only one space removed. And the trick here is to take those 4 duplicates, rotate 2 of them and put them together so that those 3 spaces there can easily be tiled with one more tromino. We've got as many trominos as we like to use, leaving only one space untiled, no overlaps, no further spaces. So we've proved that it's also true for the n equals k plus 1 case. So if we just check that out again, because I think it's nice. If we look at the n equals k plus 1 case, take 4 copies of the k-sized grid, rotate 2 of them and push them together, we can add one more tromino and prove that it's true for n equals k plus 1. All that's left to do is make a final statement. We proved that the proposition was true for n equals 1, and that if it was true for n equals k, it was also true for n equals k plus 1, and so by mathematical induction we've proved that the proposition is true for all integer values of n greater than or equal to 1. It's a proof that I really like.